solve some problem of fake about one gold artifact from Byzantine time, which was purchased by the curator of the Museum of Berlin, and in which several elemental contributions seems to be of very recent period. Then it was asked to us to measure several points on this object in order to give the composition mainly of the soldiers. The most part of my activity was the study of gold from everywhere in the world, in order mainly to study the soldering procedures, and since about 10 years, the way it was possible in Central America to produce very wonderful and very big objects, weighing about 1 kilogram, 2 kilogram, 10 kilograms, seeming to be pure gold, and in fact they contain only 40% of gold. And when the Spaniards came in Central America in the 16th century, and they bring back in Spain all this treasure in order to fuse it, they found it was nearly pure copper. Then I will explain how it was possible to measure this enrichment of concentration of gold at the surface of artifacts. Most of you are at the beginning of a new type of study. Then I will try to be not too precise in physics, and perhaps to discuss the physical problems later with physicists. I will also probably speak about another problem, the use of the accelerator in medicine later in the week. But I will speak very shortly on the way particles interact with material, how it is possible to use some accelerator like the one you have here in your university, a 5 megavolt machine here in Lecce or in Brindisi, and a 2 megavolt machine in Namur, then much lower, and how to apply this technology to several problems. When you have a look to some material, there is somewhere the nucleus of one atom. And you see that on the size of the spot is about 1 centimeter. Around this nucleus of the atom, there are a lot of electrons, you know probably that. And the first electron closer to the atom should be somewhere there. And for a medium nucleus, like a nucleus of copper, the size of the nucleus should be about 1 kilometer from the center of the nucleus. Then you see that material is mainly composed of vacuum. You have nearly nothing. One nucleus in a sphere of about 1 centimeter, if I enlarge by a factor, a very large factor, and the external part of the atom is at 1 kilometer from the center. There is a ratio of 10 to the power 5 between the size of the nucleus and the size of the atom. 1 centimeter for 1 kilometer. Then when with electrons, because we have only one nucleus for a lot of electrons, and the surface, the area in which the electrons are distributed is much larger than the area on which the nucleus is situated. Then when a particle interacts with atoms, then with material, we have nearly only some interaction with the electrons. If those particles are protons or alpha particles, then nucleus of several nuclei. The proton is the nucleus of the light atom, is the nucleus of hydrogen. Alpha particles is a nucleus of the helium. Then if you send those particles in material, the interaction takes place mainly with electrons, then it is a heavy particle interacting with a low mass particle. And when you send an elephant on a small dog, the elephant crosses all the dogs and spread the dogs in every direction. Then it is the same. When we send protons on material, we eject electrons, but the interaction with other elephants in the center is only 1 chance on 10 to the 10. Then the probability of interaction with the nucleus itself is very low. Then the most important interaction being with electrons, when we disturb an atom by sending protons in material, come back to the inner part, the difference in energy is emitted mainly as an X-ray. And the energy of those X-rays are characteristic of the atom which are heated by the incident protons. And when we detect those X-rays, we select those X-rays, we measure their energy, we can have some information about the nature of the nucleus, and when we count these X-rays, it's possible to make a quantitative analysis. For that, we use source. One source is a solid source with which we produce nearly all the ions we need. The other one is this one is a solid source. The second one is a gas source with which we produce only alpha particles. But it is then possible with this kind of accelerator to make a lot of things. Once, to make analysis of materials by sending proton, by sending alpha particles on materials and then detecting characteristic X-rays, or to implant material in order to modify the surface of those materials and to produce new ones. Generally, when people are using this, it is possible to arrange the experimental setup in order to be able to collect particles which are scattered by the sample. Not easy, but it is possible to make a quantitative analysis of an unknown sample by comparison 10 microns on the sample. With the 10 micron hole here, we can reach a 1 micron spot on the sample. And the best machine installed in the world are now using microbeams of about 0.3 microns. Is it necessary to use that? I will answer probably later that it is not necessary to achieve this kind of smallness, and they can give sufficient information, mainly for archaeological artifacts, except perhaps in order to study potteries, because when you are studying potteries, you have a lot of different grains in the same pottery, and then it is necessary to isolate and to measure the concentration of elements on one isolated grain, but using an electron microscope is generally sufficient. When the incident particles interact with material, they cross a long distance in the material without deviation. When elephants interpede, but the elephant stopped after losing its energy when they are going on a straight line into the material itself. And the stopping power, I will give you only probably 2 formulas in order to be not too complicated. The stopping power, then the way the material can decrease the energy of the incident particle. Depends on several parameters. It depends first on Z1 square is the square of the atomic number of the incident particle. It is 1 for proton, it is 2 at the square for alpha particle, it is 6 at the square for an incident carbon ion. This energy is also inversely proportional to its energy. This loss of energy is inversely proportional to the energy. Then when a particle has a high energy, this particle loses a very low energy. When this particle has a low energy, it loses a maximum of energy. Then the maximum loss of energy is at the end of this trajectory, which is a linear trajectory. The defects are produced at the end of the trajectory, but the signal are produced mainly when the particles have their maximum energy, then at the surface of the material. When we radiate materials with 2 to 3 MeV protons or alpha particles, signals are coming from the surface and several defects are produced at a distance of about 30 to 15 microns. But in those regions we reach no signal. This particularity is used by nuclear medicine in order to destroy cancer cells where they are then at the end of the trajectory of the incident particle. A second point is that this energy loss is proportional also to the atomic number of the target on the atomic weight of the target, Z2 on A2. And this ratio is a ratio which is decreasing with the atomic number. For hydrogen, it is very difficult to analyze hydrogen by collecting the X-rays because hydrogen doesn't produce X-rays, but this ratio, Z2 on A2 is 1. For calcium, it is 20 on 40, then it is 1/2. But for lead, it is 0.4. Then you see that when you increase the mass of the incident particle, the charge of the incident particle, you increase the energy loss. To have a low energy loss, use protons. In order to lose a very low energy, you have to use high energy incident particles because the energy of the incident particles is in the denominator. But hydrogen decreases the energy of the incident particles much more than lead because the Z2 on A2 is 1 for hydrogen, but 0.4 for heavy ones. Then when we radiate material of different composition, we have to take care of this ratio in order to know exactly what amount of material we are analyzing. If some material contains a lot of water, in water we have 2 atoms of hydrogen, the absorption of the incident particle gives rise to a lower range than we have a sample which is completely free from this water. Then it is a problem which can be studied very easily. This formula has been given by Hans Bethe, and it is probably the oldest physicist already living. He was born in 1906, and he's 97 now, and he's still working. And this photograph was taken at the occasion of his 19th anniversary, he was producing a new paper at the American Physical Society. It is then the dean of all the physicists in the world. He was involved in the calculation of the interaction of neutrons with uranium in order to build the first atomic bomb half a century ago. Then to summarize very shortly what I have said by comparison with electrons, when you irradiate a material with electrons, electrons has the same mass, incident electron has the same mass than the electrons of the material, then the scattering is nearly similar to the scattering of one billiard ball on other billiard ball. They can be scattered in every direction. You see that the interaction takes place in some region which is nearly circular around the point of impact, and the region of interaction is about 1 micron. When you send 2 MeV protons on the same material, you see that the trajectory is nearly linear, except that at the end of the trajectory, we have the possibility to have some scattering. And why you have some scattering at the end of the trajectory? At the end of the trajectory, the velocity of the incident particle is lower than at the beginning. Then each particle passes a longer time around the nucleus, and then as the time of interaction is longer, the possibility of scattering is also more probable. If I take again this kind of representation, I can say that if we send protons in vacuum and we put at the end of the accelerator a thin foil of material, a very thin one, about a few microns, we use mainly Namur aluminum foil. I will give you the reason in a moment. Those particles cross this foil of aluminum and they can reach several distance in material and then in the air. When we send 2 MeV protons across a foil of aluminum of about 10 microns, it's possible to see the beam of protons coming up to 12 to 15 centimeters in the air. Then if we put on the trajectory of those protons one sample, we will irradiate this sample in outside vacuum, then the size of the sample has no importance. The maximum size is the size of the doors of the laboratory to which the sample can be introduced. And you can move your sample in order to irradiate one specific position in order to have information without introducing the material in vacuum. There are a lot of advantages. You see that it is not possible to do the same thing with a beam of electrons due to the interaction of electrons with material, because the scattering in every direction. And it is possible to do with protons. The material is then not heated, because when you send particles on material, you heat the material if the material is kept in the vacuum. It is not heated because the air can remove the heat deposit. As in the air, you have also ions. You have several ions, negative and positive ions in the air. When you irradiate the material with positive particles, it's possible to remove electrons. Then we have a charge of the samples if the sample is an insulator. But if this insulator is irradiated with charged particles which are positive, protons, we add positive charge, you remove negative charge by ejecting electrons, then you increase the positive charge on the sample itself. But as you have a lot of other charge in the air, if you irradiate your sample and it is positively charged, the negative ions from the air will be attracted by this positive charge, and the charge will disappear. Then you can irradiate insulator without any trouble when you irradiate the material in the air. When you introduce your material in the vacuum, it is possible that if the material contains some water, I think about some papers on books and so on, you have always water inside, the water will be evaporated. If you put your piece of paper in vacuum, if you irradiate outside vacuum, you have no problem. Then you have a lot of advantage, nearly without disadvantage, by irradiating the material outside vacuum. And this kind of technology has been probably invented in Namur in '69. Then it is more than 35 years ago. And it is now used everywhere in the world. Then to summarize, suppose you have to detect X-rays coming from material. We send protons through a tin foil of aluminum. We irradiate some sample, and we have the possibility to detect X-rays in two different detectors. This one mainly detects the X-rays coming from the sample itself, and we have another one which focuses on the distance between the exit foil and the sample to see only this 1 centimeter crossed by the protons in the air. In the air you have neon, and when you irradiate neon you produce X-rays of neon. And if you detect the number of X-rays of neon in the second detector, you have a measurement of the intensity of the incident beam. Then it is a secondary way to measure the number of protons which are arriving on your sample by comparison with the number of protons which were arriving on a reference sample by using only the signal of near. If you need now to analyze materials like sodium, aluminum, magnesium, silicon, those materials are used as pigments for paintings. Once you cannot use an exit foil of aluminum because the exit foil of aluminum will produce X-rays of aluminum, which is also perhaps in your material itself. The X-rays of aluminum, as aluminum is a low atomic weight material, the energy of the aluminum X-ray is low. Then it is highly absorbed in the air itself. The way to avoid that is to replace the exit foil of aluminum by an exit foil of plastic containing only carbon and hydrogen, and to try to send some helium flow in the region of the target in order to replace the air by helium, in order to replace some materials with an atomic weight of 16 and 14 sodium, oxygen and nitrogen by helium, then in order to reduce the absorption of X-rays. And this kind of technique is used by Piero Mando, it is not because it is an Italian one, I gave the figure in the wrong direction. It was invented by Piero Mando in Florence, and you know perhaps that Piero Mando is mainly involved in the study of manuscript, mainly the manuscript of Galileo. You know perhaps, was it?
Yeah, he was here.
He was here, yes, we could talk about. Then he tried to recognize the ink used by Galileo in his scientific writing by comparison with his book notes, in which he noted when he was purchasing potatoes and so on, because probably the same way he was using the same ink. Then it is the same technology used here in Florence. When we need to have a large amount of information, it is possible to put around the sample a lot of detectors. Low energy X-ray detector, but with fast detection activity. Bigger detectors of X-ray and bigger. And in this system we have 4 detectors for low energy X-ray but with high counting rate, for low energy X-ray but with a low counting rate, for high X-ray energy and also for gamma rays, in order to be sure that when we radiate the material, we detect information always from the same spot. One technique to analyze material is Rutherford backscattering. I will give only one example here. It was a succession of coatings of gold, aluminium, gold, and so on. When some incident particle interact with gold, it is like a pea, a small pea interacting with some elephant. When this incident pea interacts with aluminium, it is something like a dog. And the energy which is backscattered on gold is higher than the energy which is scattered by another one. Then when you have a succession of heavy elements, light elements, and so on, you see that you can distinguish the first layer of gold. The second layer is a layer of aluminium, but the energy scattered on aluminium is lower, and the signal of aluminium is in this region. For the second gold, we have here the signal. For the second aluminium, the signal is there, and for the third gold, the signal is there. You see that the signals are not squared, but the signals are smooth knit in the surrounding, except at the surface. That the surface of gold, that the gold of the last layer of the first gold coating. Then we have nothing here because we have no gold, and the signal we have here is the signal produced by the scattering of the second interface of gold. But you see that some signal is missing in those regions. It is because we have some diffusion of gold in aluminium or aluminium in gold. Then, in order to make this kind of measurement, it is possible to do Rutherford backscattering. Then it is the elastic scattering of the incident particle on the nucleus. But the probability to make this interaction is very low, because the surface of the nucleus is very small by comparison with the surface of the atom, and when the atom is reached by the incident particle, the emission of X-rays is the most important interaction procedure. Then it is possible to use this kind of technology. If you are physicists, I will speak about that later on. Materials with incident particles. It was a big problem for us to convince curators of museum to have some material in order to be analyzed. And the proof is given here. We have used exactly the same technology in order to study the migration of fluorine in the tooth enamel in vivo. We irradiate the tooth of the person directly in the mouth. And you see here the tube of the accelerator, the people in place, the gamma ray detector in order to check the presence of fluorine, and
Was he
we
a
have
student?
what?
Was he a student or?
No, it's a collaborator, but
It was.
but in 68 it was myself. But from 68 up to 2003, my face has changed so much that I don't show you that. And this one is a very new one, because we are now studying this kind of problem with some dentists of the University of Brussels. I give you only 2 words or 3 words on the subject, because this is probably very amazing for you. It is known that when you irradiate the teeth with a laser beam, the number of caries will decrease. There is a big problem between dentists. Is it necessary to irradiate the teeth with a laser beam before applying fluoride or after applying fluoride? And we have shown that it was necessary to apply fluoride. Fluoride migrates through the organic material between the small piece of crystals of your enamel, and then it diffuses in the teeth laterally. And then by irradiating after the fluoration your teeth with a laser beam, you close the channel, and then you keep inside the enamel the excess of fluoride. Then you must be convinced that it is not dangerous, because the time of measurement of the fluoride concentration in the tooth is about 30 seconds. We have irradiated some phantom containing a lot of detectors in order to see if the brain of the people would be not reached by very dangerous gamma rays or something else. We use low energy protons in order to not produce too much neutrons, and you produce probably no neutrons. We have tried to detect it, and we have seen that after several hours of irradiation with a beam which is 100 times higher than the beam we use for the measurement of fluoride, we don't see anything in several detectors we had in a phantom, which is a reproduction of the brain. And then you see every people has his own system in order to plug ourselves to the end of the accelerator in order to irradiate exactly the same position on the teeth during the treatment, just after the fluoride treatment, 1 hour after, 2 hours after, 1 day after, 1 month after, 6 months after, 9 months after. And those measurements with the laser beam has proved that after 9 months of experiment, the increase of fluoride in the tooth was about 60%. Then the treatment is very effective. It will be presented in the first applied physics meetings in October in Badajoz. You have probably the information about it. A few words.
Do you have a project about this kind of things?
We have a project,
Yes.
but only a private project between the 2 centers, the Center of Dentistry of the University of Brussels and the University of Namur. We have studied this migration of fluoride in the tooth 25 years ago. Then the problem was left up to the moment that this laser treatment was a new procedure to increase the effectiveness of the treatment of fluoride. The enamel is hydroxyapatite, in which you have OH ions, and when you replace the OH ion by a fluoride ion, you strengthen the enamel itself. I was mainly interested in the past by the measurement of gold artifacts, and when we have a gold artifact, we have not only gold in the artifact, because gold is soft, but generally gold artifacts contain silver and copper. And that is a spectrum obtained when we irradiate a sample containing gold, silver, and copper. We see three signals of gold: gold L alpha, gold L beta, gold L gamma, 1, 2, and 3 lines, 2 lines of silver, 2 lines of copper, but you see also lines of zinc. Why do you see lines of zinc? Zinc is not present in this gold artifact. But in gold artifact, the concentration of gold is high. If the concentration of gold is high, the signal of gold is very high. Then, if the signal of gold is very high, we have to irradiate a very, very, very long time in order to be able to measure trace of copper or trace of silver. Then it is necessary to decrease selectively the intensity of the gold lines. And by putting between the target and the detector a thin foil of zinc, we selectively decrease the intensity of the gold signal in order to increase proportionally the signal of copper and the signal of silver. Then it is only an experimental artifact, but when the X-rays of gold are absorbed in the zinc, they ionize the zinc, and when they ionize the zinc, they produce X-rays of zinc. One big laboratory in the world was ignoring this fact, and at the place where we have a small signal of gold, the line is called the LL line of gold, and the LL line of gold is exactly at the same energy as the key alpha line of zinc. And this very known laboratory say in each sample we have irradiated, we have found 700 ppms of zinc. It was not zinc, but it was this satellite line of gold. Then when people make analysis, they have to take care to a lot of things, mainly traces, line of low intensity which can interfere with other elements in order to not attribute that. The sensitivity with PIXI is very good, and you see that when you have no matrix effect, you can reach, when you analyze material with Z between 20 and 30, then between calcium and copper, it is possible with an energy of 2 MeV to reach a sensitivity which is lower than 1 ppm, 1 part per million. Then it is a very sensitive method. And you see also that by detecting the L lines of higher elements, it is also possible to achieve this kind of sensitivity. The method is sensitive provided you have not a huge signal coming from the matrix. If you have signal coming from the matrix, like in an iron matrix, you see that the number of microgram per gram, then it is the number of ppm, the sensitivity, is around 10 ppms for chlorine and for arsenic in iron, but the signal of iron is so important that even when you're using filters in order to kill the majority of the signal of silver, the sensitivity for the measurement of chromine, vanadium, titanium, nickel, copper, and zinc is much lower than the one which is given in the table. I will stop here for 10 minutes, and then to use this kind of technologies, and mainly PIXI, to make analysis of several elements. I will speak about bronzes, I will speak about gold, and if you want, if I have some time, 1/4 more, to speak very shortly on the way the pyramid of Cheops was built. It's a very big problem. I expect to speak on that problem more largely when I will speak about medicine, because during the break I asked you to make a very simple calculation. The pyramid of Cheops has a volume of 2,600,000 cubic meters, 2.6 10 to the 6 cubic meter. And this pyramid was built in 26 years. Not exactly 26, but 2.6 million cubic meter in 26 years will allow you to make a calculation easier. Then calculate how much blocks per year, how much blocks per day, how much blocks per hour. They are to be put on the side, and you will understand that the construction of the pyramid of Cheops was not the one which is reported in all the Egyptological books. It is not the procedure. We have rediscovered this procedure, and I will give you some information about that using analysis of several specimens, if we have some time, but mainly bronze, gold, and perhaps pyramids. Romando from Florence, the director, which was Dupuis in the laboratory of the Louvre in Paris, Yanis Maniatis in Athens, Jeff Bryan of Oxford, and myself, to launch some network to make archaeometry, to use physical and chemical methods in order to study archaeological material. But the project was rejected. It was not sufficiently physics, not sufficiently chemistry, not sufficiently archaeology. And it is very difficult. And I think that the new section in this university is a very powerful one. For the future, it will be difficult to obtain something, but we need to protect our cultural heritage, to have people involved in the three disciplines. And I think that the first tentative here in Lecce to organize this kind of university section would be powerful. But when you are making when you are making some archaeometrical measurement, and you will take a very strong position as a physicist, you can get very interesting job in physics. Making some work with me on archaeometry. We were studying together the way gold artifacts were sold in antiquity. When he asked me after his graduate studies to continue and to make a PhD, I said it is impossible to find a job with such kind of soldering, which was invented in Italy by Etruscan in the north of Italy 2 millennia and 500 years ago. I will speak about that in my example. And then I am happy that this section exists here in Lecce. I have some proposal to collaborate, I will do it later. But as the network was not successful, we have introduced the possibility to be involved in cost action. Cost means, for the European community, collaboration in science and technology. CO or ST, collaboration in science and technology. And then we had some kind of network, but without any financial support from the European community, particle-induced X-ray emission. It is very similar to X-ray fluorescence, but we replace the incident X-rays in X-ray fluorescence by a beam of protons in order to make particle-induced X-ray emission. And as I was mainly involved in the study of gold, I give you here the situation of the intensity of the signal we are collecting when we are irradiating material containing gold, silver, and copper. Suppose we are using 3 MeV protons. We have here the cross-section, then the probability for the production of X-ray. You have to take into account that several times your reference sample is a flat one, but you have to analyze some wire, which is some circular one. Then you see that the outgoing path of X-rays in the material, decoration, 28 decoration, and those decorations are composed by a cylinder here, a first hemispherical cap, and a second one. I think I have a good representation in the second slide. You will see. The first one will show you probably it was possible to analyze also some potteries, and you see the beam line of protons. The protons are not illuminating the material. When we extract the proton beam in the air, we see a small information of blue light in the air, but it was amplified by blowing some smoke of cigarette into the beam itself in order to produce this luminosity. And you see there that some pottery was irradiated with a beam of about 5 millimeters in diameter. It was a large one. The next one is probably these wonderful artifacts I have here. The next one will show you some detail. It is the detail at the top right. You see the cylinder, one soldering here with something missing there, one soldering there with something missing also. But you see here also the line, because it was something like this. This cylinder was made by this way. Without any soldering of this part. And it was something like this. And the hemispherical cap was soldered on this piece of gold. You see there this line between the two borders, and you don't see this line in this region there. I will later